Welcome to our deep dive into electromagnetic induction, a cornerstone of modern physics and technology. In this chapter, we'll explore the fundamental laws, key concepts, and practical applications that make electromagnetic induction so vital. From the pioneering work of Faraday to the everyday devices powered by these principles, you'll discover how changing magnetic fields can create electric currents, and why this phenomenon is at the heart of generators, transformers, and more. Let's embark on this journey to understand how invisible forces shape the world around us, powering everything from household appliances to massive power grids. Start with Faraday's laws of electromagnetic induction. Michael Faraday discovered that a changing magnetic field within a closed loop induces an electromotive force, or EMF, in the wire. His first law states that whenever the magnetic flux linked with a circuit changes, an EMF is induced. The second law quantifies this, stating that the induced EMF is directly proportional to the rate of change of magnetic flux. These laws form the foundation for understanding how electric currents can be generated without direct contact, simply by moving magnets or coils. Now let's derive the mathematical expression for induced EMF. According to Faraday's second law, the induced EMF E in a circuit is equal to the negative rate of change of magnetic flux through the circuit. Mathematically, this is expressed as E equals d phi/dt, where phi is the magnetic flux. The negative sign, as we'll see, is explained by Lenz's law. This formula is crucial for calculating the EMF generated in various practical situations, such as moving a conductor through a magnetic field or changing the area of a coil. Lenz's law provides the direction of the induced EMF and current. It states that the induced current always flows in such a direction that it opposes the change in magnetic flux that produced it. This is why the negative sign appears in Faraday's law. Lenz's law is a direct consequence of the conservation of energy, ensuring that the induced current creates a magnetic field opposing the original change. This principle is essential for understanding the behavior of circuits and devices that rely on electromagnetic induction. Conservation of energy is at the heart of Lenz's law. When a current is induced, it always acts to oppose the change that caused it, preventing the creation of energy from nothing. For example, if you try to push a magnet into a coil, the induced current creates a magnetic field that resists the motion. This means you must do work to move the magnet, and that work is converted into electrical energy. This elegant balance ensures that energy is neither created nor destroyed, but simply transformed from one form to another. Self-induction is a phenomenon where a changing current in a coil induces an EMF in the same coil. When the current through a coil changes, the magnetic field around it also changes, which in turn induces an EMF that opposes the change in current. This self-induced EMF is a key concept in understanding how inductors work in electrical circuits, especially in devices that need to control or limit the rate of current change, such as in filters and transformers. Coefficient of self-induction, often called inductance and denoted by L, measures how effectively a coil induces EMF in itself when the current changes. It's defined as the EMF induced per unit rate of change of current. The unit of inductance is the Henry H. A higher inductance means a greater opposition to changes in current, which is why inductors are used to smooth out fluctuations in electrical circuits. Mutual induction occurs when a changing current in one coil induces an EMF in a nearby coil. This principle is the basis for transformers and many types of sensors. When the current in the primary coil changes, it alters the magnetic field, which then induces an EMF in the secondary coil. The efficiency of this process depends on the coils, orientation, distance, and the core material between them. Coefficient of mutual induction, or mutual inductance M, quantifies how effectively a change in current in one coil induces an EMF in another coil. It's defined as the EMF induced in the secondary coil per unit rate of change of current in the primary coil. The unit is also the Henry H. High mutual inductance is desirable in devices like transformers, where efficient energy transfer between coils is essential. Inductors store energy in their magnetic fields when current flows through them. The energy stored U in an inductor is given by the expression U equals 1/2 Li2, where L is the inductance and I is the current. This stored energy can be released back into the circuit when the current decreases. Understanding this concept is crucial for designing circuits that need to manage energy efficiently, such as in power supplies and radio transmitters. D-currents are loops of electric current induced within conductors by changing magnetic field. These currents flow in closed paths, often causing unwanted heating and energy loss in metal components. However, eddy currents also have useful applications, as we'll see in the next scene. Understanding how and why eddy currents form is important for engineers who design electrical machines and devices. Despite their tendency to cause energy loss, eddy currents have several practical applications. They are used in electromagnetic braking systems, induction heating, and metal detectors. For example, in trains, eddy current brakes provide smooth and contactless stopping power. In manufacturing, induction heating uses eddy currents to heat metals quickly and efficiently. These applications show how a phenomenon that can be a nuisance in some contexts can be harnessed for useful purposes in others. Alternating EMF refers to an electromotive force that changes direction and magnitude periodically. This is the principle behind alternating current, AC electricity, which powers most homes and industries. Alternating EMF is produced by rotating coils in magnetic fields, as in generators. The periodic change allows for efficient transmission of electricity over long distances, making it a cornerstone of modern power systems. Let's derive the expression for EMF induced in a rotating coil. When a coil rotates in a uniform magnetic field, the magnetic flux through the coil changes sinusoidally. The induced EMF E is given by E equals nab omega sin omega, where n is the number of turns, A is the area, B is the magnetic field strength, and omega is the angular velocity. This formula explains how generators produce alternating current by simply rotating coils within magnetic fields. Transformer is a device that transfers electrical energy between two or more coils through electromagnetic induction. It can increase or decrease voltage levels, making it essential for efficient power transmission. Transformers are found in nearly every electrical grid, allowing electricity generated at power plants to be transmitted over long distances and then stepped down for safe use in homes and businesses. Principle of a transformer is based on mutual induction. When alternating current flows through the primary coil, it creates a changing magnetic field, which induces an EMF in the secondary coil. The ratio of the number of turns in the primary and secondary coils determines whether the voltage is increased or decreased. This simple yet powerful principle enables the safe and efficient distribution of electricity. Efficiency of a transformer is the ratio of output power to input power, usually expressed as a percentage. High efficiency means that very little energy is lost during the transfer. Modern transformers are designed to minimize losses due to resistance, eddy currents, and magnetic leakage. Efficient transformers are crucial for reducing energy waste and ensuring reliable power delivery. Transformers are not perfectly efficient. They experience several types of losses. These include copper losses due to resistance in the coils, iron losses from alternating magnetic fields in the core, and leakage losses when some magnetic flux escapes the core. Engineers use special materials and designs to reduce these losses, such as laminated cores to minimize eddy currents and high-quality conductors to lower resistance. Generator is a device that converts mechanical energy into electrical energy using electromagnetic induction. By rotating a coil within a magnetic field, generators produce an EMF which drives current through an external circuit. Generators are the backbone of power plants, providing electricity for homes, industries, and cities around the world. AC and DC generators both use electromagnetic induction, but they differ in how they deliver current. AC generators, or alternators, produce alternating current by allowing the output to reverse direction periodically. DC generators use a commutator to ensure the output current flows in one direction. Each type has its own advantages and applications, with AC generators dominating power generation and DC generators used in specialized equipment. Electromagnetic induction is fundamental to modern technology. It enables the generation and distribution of electricity, the operation of transformers, and the functioning of countless devices. Without it, our world would lack the power infrastructure that supports communication, transportation, healthcare, and industry. Understanding electromagnetic induction is key to appreciating how science drives technological progress. Michael Faraday's experiments in the early 19th century revolutionized our understanding of electricity and magnetism. By moving magnets through coils and observing the resulting currents, Faraday demonstrated that electricity could be generated from magnetism. His meticulous work laid the groundwork for the development of electric generators and transformers, changing the course of science and industry forever. Magnetic flux is a measure of the total magnetic field passing through a given area. Visualizing flux lines helps us understand how changes in magnetic fields induce EMF in coils. When the number of flux lines through a loop changes, either by moving the magnet or the coil, an EMF is generated. This visualization is crucial for grasping the core ideas behind electromagnetic induction. Negative sign in Faraday's law isn't just a mathematical detail, it reflects a fundamental physical principle. It ensures that the induced EMF always acts to oppose the change in magnetic flux as dictated by Lenz's law. This opposition is what maintains the conservation of energy and prevents perpetual motion, anchoring electromagnetic induction firmly within the laws of physics. Imagine pushing a bar magnet into a coil of wire. As the magnet enters, the magnetic flux through the coil increases, inducing a current. If you try to pull the magnet out, the flux decreases and the induced current reverses direction. This simple experiment vividly demonstrates Faraday's and Lenz's laws in action, showing how motion and magnetism combine to generate electricity. In electrical circuits, self-induction plays a critical role in controlling current changes. When a switch is opened or closed, the sudden change in current induces an EMF that opposes the change, sometimes causing sparks or voltage spikes. Engineers use inductors to manage these effects, protecting sensitive components and ensuring smooth operation. Mutual induction is the principle behind many everyday devices. For example, wireless chargers use mutual induction to transfer energy from a charging pad to a device without direct contact. By aligning coils in both the charger and the device, energy is efficiently transferred through changing magnetic fields, showcasing the practical power of electromagnetic induction. Inductance isn't just a theoretical concept, it's used in countless real-world applications. Inductors are found in power supplies, radio transmitters, and even car ignition systems. Their ability to store and release energy makes them invaluable for managing current and voltage in electronic circuits, ensuring devices work reliably and efficiently. While eddy currents can cause unwanted heating and energy loss, engineers have developed ways to minimize their effects. Laminating the cores of transformers and motors, for example, restricts the flow of eddy currents, reducing energy loss and improving efficiency. These design strategies are essential for building reliable and energy-efficient electrical machines. Alternating current, or AC, is the standard for household and industrial electricity. Its ability to be easily transformed to different voltages makes it ideal for long-distance transmission. Thanks to electromagnetic induction, AC can be generated, transmitted, and used efficiently, powering everything from lights to large appliances. Rotating coil is at the heart of generator design. As the coil spins in a magnetic field, the changing angle between the coil and the field causes the magnetic flux to vary sinusoidally. This variation induces an alternating EMF, which is then harnessed to supply power to electrical grids. The simplicity and effectiveness of this design have made it a mainstay in power generation. Transformers can either increase step-up or decrease step-down voltage levels. Step-up transformers are used at power plants to raise voltage for efficient transmission, while step-down transformers lower voltage for safe use in homes. This flexibility is vital for modern power systems, ensuring electricity is delivered safely and efficiently. The core of a transformer is designed to maximize magnetic coupling between coils while minimizing losses. Using soft iron and laminating, the core helps concentrate the magnetic field and reduce eddy currents. These design choices are crucial for achieving high efficiency and reliable operation in power distribution networks. To further minimize losses, transformers use high-quality materials and precise engineering. Reducing resistance in the coils, optimizing core shape, and using advanced cooling methods all contribute to better performance. These improvements help ensure that as much energy as possible is delivered to where it's needed. Generators come in many types and sizes, from small portable units to massive machines in power plants. They can be powered by various energy sources, including steam turbines, water, wind, and internal combustion engines. Regardless of the source, all generators rely on electromagnetic induction to produce electricity. AC generator typically consists of a rotating coil, a magnetic field, and slip rings to transfer the generated current. As the coil rotates, the magnetic flux through it changes, inducing an alternating EMF. The slip rings ensure that the output current alternates smoothly, making AC generators ideal for large-scale power production. DC generators use a commutator instead of slip rings. The commutator reverses the connection of the coil to the external circuit every half turn, ensuring that the output current flows in a single direction. This makes DC generators suitable for applications requiring steady unidirectional current, such as battery charging and electroplating. Main difference between AC and DC generators lies in their output. AC generators produce current that changes direction periodically, while DC generators provide a constant direction. This distinction affects how each type is used, with AC favored for power grids and DC for specialized industrial and electronic uses. Electromagnetic induction isn't just for generating electricity, it's also the principle behind electric motors. In a motor, electric current in coils produces a magnetic field that interacts with a permanent magnet or another coil, causing rotation. This process is the reverse of what happens in generators, highlighting the deep connection between electricity and magnetism. Wireless power transfer is an exciting application of electromagnetic induction. By using coils and alternating currents, energy can be transmitted without wires over short distances. This technology is already used in wireless phone chargers and is being developed for electric vehicles and other applications, promising a future with fewer cables and more convenience. Induction cooking uses electromagnetic induction to heat pots and pans directly. An alternating current passes through a coil beneath the cooktop, creating a changing magnetic field. This field induces eddy currents in the metal cookware, generating heat quickly and efficiently. Induction cooking is fast, safe, and energy efficient, making it increasingly popular in modern kitchens. Magnetic levitation, or maglev, trains use electromagnetic induction to float above the tracks, eliminating friction and allowing for incredibly fast travel. Powerful electromagnets create changing magnetic fields that induce currents in the train's guideway, generating lift and propulsion. This cutting-edge technology demonstrates the remarkable potential of electromagnetic induction in transportation. Magnetic resonance imaging, or MRI, is a medical technology that relies on electromagnetic induction. Strong magnetic fields and radio waves induce currents in the body's tissues, allowing detailed images of internal organs to be created. MRI is a non-invasive, powerful diagnostic tool that has revolutionized healthcare. From the power that lights our homes to the trains we ride, and the medical scans that keep us healthy, electromagnetic induction is everywhere. Its principles are woven into the fabric of modern life, making possible the conveniences and technologies we often take for granted. Understanding this phenomenon helps us appreciate the invisible forces that power our world. Summary: electromagnetic induction is a fundamental principle that underpins much of our modern technology. From Faraday's groundbreaking experiments to today's advanced applications, the ability to generate and control electricity through changing magnetic fields has transformed society. As we look to the future, ongoing innovations promise to unlock even more potential, making electromagnetic induction an enduring force in science and technology.